Well, it's just turned to the hour. Welcome to everyone in the UK or in the United States or elsewhere around the globe to the third of our Challenger conversations hosted by the Scottish Association for Marine Science. My name is Gillen Wood. I'm at the University of Illinois and an oceans historian working on a book on Challenger. And just as a quick plug, for a new iteration of the Challenger Expedition website that is now available for your own perusal and exploration on the SAMS website. You might remember that the first edition of the Challenger website was launched a year ago this week. And we now have Challenger Expedition 2.0 with an improved and updated map interface for exploring what Challenger found and where they found it. All of the 360 stations that they visited are there on the map. And also, perhaps the most important improvement of the site is that the species search engine is now searchable by modern names. So no one is expecting you to know the obsolete Challenger name for a specific species. You can enter a modern name, and the map will show you where those species were found. So moving on to the subject of our third conversation here. And thanks for joining us. It's now minerals from the sea. We'd like to welcome three guests to our conversation: Melissa Ryan, Nick Owens, and Andrew Sweetman. And I'd like to begin by introducing Melissa Ryan, who will give a few opening remarks and tell us a little bit about herself and her own experiences in deep sea research and also ocean education. Melissa is the Vice President of the Global Foundation for Ocean Exploration. She's a scientist, ocean explorer, and educator with more than 25 years of experience in the oceanographic and education fields. She worked for 7 years as an education specialist for NOAA's Office of Ocean Exploration and Research, where she managed a national professional development program on ocean science and exploration for educators. So I'll hand it over to you, Melissa.
Thank you. Welcome, everybody. Yeah, I'm excited to be here. I've been interested in Challenger for about 20 years now, since working with the College of Exploration on their online workshop in 2004. And as part of that, I wrote some classroom-ready lessons for teachers about oceanography in the late 1800s compared with oceanography today. As Gillen mentioned, I'm currently Vice President of the Global Foundation for Ocean Exploration. We are a nonprofit based in Mystic, Connecticut. And we design, build, and operate deep sea remotely operated vehicles, ROVs, that are capable of going to 6,000 meters. And the very cool thing is that we share those dives in real time throughout the internet. So when the vehicles are diving on the bottom, you can tune in to the Okeanos website and see what the robot is seeing in like a 1.5 second delay, and hear the scientists talking about it and make the discoveries with us as they're happening. I should mention that we do work with NOAA's Office of Ocean Exploration as our primary partner, and we're on their ship, the Okeanos Explorer. We have a team of filmmakers who tell the stories of deep ocean discoveries. And I should point out that we explore just for habitat characterization. We are not involved in the deep sea mining at all. We just go and see what's there and leave that for follow-on researchers who want to return to a certain site. So again, pleased to be here. Welcome, everybody. And I will hand it back to Gillen.
Thanks, Melissa. So the two of us will be, as co-chairs, will be hosting a Q&A session after the two presentations by Nick and by Andrew. And so we invite you to put questions that come to mind in the Q&A, or if you have comments or links to offer, please put those in the chat. So it's my pleasure now to introduce Nick Owens, perhaps a man who doesn't need a lot of introduction, but I'll do it anyway. But first, a little bit of background to this particular episode or episodes in Challenger's Voyage that we are harking back to today. we're approaching Christmas, and the Challenger spent the Christmas of 1875 in the Patagonian fjords. They had just concluded their Pacific crossing, and from Japan through Hawaii, south to Tahiti, and then to Valparaiso. And it took them most of the year of 1875. Now, one of the features that they recognized as the most important of that crossing was their discovery of vast fields of what they called manganese nodules. And descriptions of these nodules, they dominate the diaries and the logs of the naturalists on board the Challenger. They were intrigued and fascinated by the volume and the nature of these nodules, the fact that they were enveloped around shark's teeth or fragments of shells or whale ear bones. And so there's, for anyone interested in the Challenger literature, there was already in the 1870s, during the voyage, a sort of a realization that this was a monumental discovery on the deep sea floor. And the first the first important description of the manganese nodules, of course, we find in John Murray's report from 1892 on the deep sea deposits, which is a landmark volume in marine geology. Now, to tell us a great deal more about this is Nick Owens. Professor Owens is the director of the Scottish Association for Marine Science, as we know. He's a marine biogeochemist with particular interest in nutrient cycling, stable isotopes, and biogases. His research has taken him to all parts of the world ocean, requiring him to spend many years at sea on research vessels. I think, Nick, you've calculated it at something like 4 or 5 years in total if you were to add up all your days at sea. Very impressive. Now, a long-standing interest Nick has had in the career of John Murray, who was the pioneer marine geologist aboard HMS Challenger. And he's made a personal promise to me to write Murray's long overdue biography, though this project might have to wait till his retirement. So we'll hear a lot more now about Murray, about manganese nodules, and also the seasonally appropriate Christmas Island speculation. So over to you, Nick.
Nick, you're muted. And your screen is trying to share.
Can you hear me now? Can you see my screen?
We can hear you. You can't see the screen just yet.
I can't see where it's gone. I clicked share my screen. It all worked beautifully before. I'm getting rid of everything. How's that? I don't know what I did, but there should be a screen there now.
Yes, there you go.
Excellent. I don't quite know what happened, but whatever it was, it worked. Anyway, thank you very much, Gillen. Yes, I hope to fulfill my promise on John Murray. But yeah, certainly you mentioned my interest in Challenger. This is a very famous sort of painting of Challenger. I've been interested in Challenger for 40 odd years now. I was fortunate to get what was known then, it's no longer in existence, a Royal Society fellowship for traveling called the John Murray Traveling Studentship. And having won that, I thought, well, I better find out who John Murray was. And that was 40 years ago, or nearly. And I've had a great interest in John Murray ever since. And so, as you mentioned, Gillen, I'm going to mention two things really, and that's I could talk forever on Challenger and John Murray in particular, but I'm going to focus, as you say, on two things, and that is about the manganese nodules, and suggest some interesting snippets really as a precursor for what Andrew is going to be saying, and also the Christmas Island, which is all about minerals as well, in the sense of phosphate mining. I should mention before I go any further that my slides, you will see I've got this banner down the left-hand side, and these are I'm very generously been allowed to use these by Alice Strange, who has produced some wonderful artwork around the Challenger expedition. And for those of you who know SAMS, you'll recognize some of these images are in our foyer. So I'm very grateful to be able to use that. But one of the things that preparing for this talk allowed me to do actually was relive actually getting my hands wet and dirty, so to speak, on the Challenger reports. So here are a couple of the Challenger reports on my desk that's actually behind me now. And it's always a fabulous pleasure to actually go back to the original source of the reports from the Challenger. And the one that you see there with the map, we'll see a close-up of that map in a minute, is the report that Gillen's just mentioned, and that was the report that was written by Murray on the deep sea deposits where the manganese nodules were described. But that just as a slight precursor, because one of the things that I was interested in doing and thinking about this talk was, when were the nodules actually really first described? And I'll come on to some dates about that in a minute. But where I went to in sort of pursuing that question was to some precursors of the Challenger expedition itself, and that is these two very small Royal Naval ships, HMS Lightning and HMS Porcupine. These carried out some surveys primarily around sort of the west coast of Britain, north and Scotland and off Ireland, where this almost a craze really of dredging the deep sea was. So it's kind of started out deep sea dredging with, sort of rather well-off naturalists and gentlemen scientists and the like. And it started to get more sort of mainstream science with professors, and particularly some of the professors based out in the University of Edinburgh. And one of these in particular, the name here you see on here, W.B. Carpenter, they managed to persuade the Royal Navy to deploy some ships rather than using private yachts. They managed to persuade the Navy. These are two very small ships, but nevertheless, they were naval vessels to go deep sea dredging. And I'd never really looked before, but I thought, I bet some of the earliest descriptions of deep sea nodules, of manganese nodules rather, was going to be in this very famous book by Wyville Thompson, primarily, and Jeffreys and Carpenter, written in 1873. So before the Challenger ever set to sea. And you know what? There's no mention of manganese nodules in this book. I specifically looked for this, and I can't find any. However, what is interesting about this particular book is just in the preface, some really, I think, given what we now know about Challenger, this was written by Wyville Thompson in the preface, noting the date before the Challenger actually set sail, and he was talking about the purpose of the work that went into this book, and he says he would like to induce those who have the proclivities and the opportunity to penetrate farther into the new and strange region on whose borders we have had the good fortune to have been among the first to encroach. So what he's actually prefacing here is actually the Challenger about to set sail, because he wrote this on the 2nd of December 1872, and Gillen has pointed out actually the Challenger actually set sail just 2 or 3 days before Christmas in 1872. And then while I'm writing, so he's writing this preface, and while I'm writing, a noble ship is lying at Sheerness, that's the Challenger, equipped for scientific research under his wise and liberal directions, as no ship of any nation was ever equipped before. So here was Wyville Thompson, the chief scientist on the Challenger. A couple of weeks before joining the Challenger, he basically published this book, The Depths of the Sea. And I really wished he'd actually mentioned manganese nodules in it, but he didn't, as we'll come on to. Anyway, so did happen, as we have heard, is that manganese nodules were in fact discovered on the Challenger and the report that Gillen has mentioned is this one, the report on the deep sea deposits. And we've got John Murray on the left, and we've got the Reverend Reynard on the right here. And it was written 1891, 1892. Now, this was one of the last reports of the Challenger series. There were 50 volumes. This was the last but one report. It was written whilst by this time John Murray, who took over from Wyville Thompson, saw the publication of these 50 volumes through using his own money towards the end. And he writes in his own preface to this volume, clearly fed up actually, that he'd spent 20 years of his life preparing this volume. And so one of the things about this report is it covers lots of things besides what's happened on the Challenger. But anyway, this is this really wonderful book, and it's worth looking at it if you get a chance. And for those of you in SAMS, there is a full set of the Challenger reports here, which you can look at. And this is just, one of the first plates in the book describing these manganese nodules, and these are various shapes and sizes and so on. Typical sort of feature of a nodule in the middle there, and some cross sections and so on. And as Gillen said, in the center of these things, there are often different nuclei that around which the nodule grows. But as I mentioned, one of the things that I was interested in doing was actually tracing back when nodules actually were very first described, because it has always been thought of as being the Challenger, and largely is. But there we are. The first record I can find anywhere of these things was in an Australian terrestrial expedition in 1847. Now, I haven't had an opportunity to read the original paper here, but I can provide the reference if anybody's interested. It's easily accessible. But as far as I know, and I'm happy to be proven wrong here, the very first sort of live description of the discovery of a nodule from the Challenger was actually on very early in the expedition in 1873 in February, in the Challenger station number 3. Now, this is for geeks, really. Challenger station number 3 wasn't, in fact, the third station Challenger did. They had 40-odd stations beforehand that were all described in Roman numerals. But the first sort of station proper was earlier on in February, and on the 18th of February, 1873, the Challenger was just off the Canary Islands. Now, I don't know, is my cursor showing on there? Yeah, okay. So what I've got here is I've cut a piece out of the map here, one of the charts from the Challenger report, and this describes the eastern Atlantic. So we've got the coast of Africa along here, the Canary Islands, and what we've got here, we've got several bits of the Challenger route. But the bit that I want to point out to you is this bit here from Tenerife. And this is where they started numbering the stations. And the stations are shown in this with these little numbers here in circles. So that's station 1, that's station 2, and this is station 3. And it was here that there was the first description of a nodule in the reports. And that was, as I say, in February there. On here, these large numbers these are the depths in fathoms. There's the current direction is on here, and the description of what the bottom was on the bottom. That's a Globigerina ooze, for instance, and so on. So that, to my mind, is the very first sort of scientific description of a nodule. Now, just taking the sort of chronology a little bit further. So we've seen this Australian one. We've got the Challenger Station 3. And they were called manganese, the first description I can find, manganese concretions. But then, interestingly, the sorts of things that Gillen mentioned in his opening remarks, they appeared right the way through the report, describing 3.5 years worth of deep sea trawling, deep sea dredging, and loads and loads of references to the nodules. And the description that Gillen gave But it's 1891 before we actually see any of that. However, and I find this quite interesting, I have to say, on the 13th of March in 1874, Wyville Thomson, the chief scientist, described some work that they were doing at station 160. So quite a long way into the voyage compared with the one station 3 that we've just seen. But you say, hang on a minute, thinking of your dates, that was in 1874 that he published this in the Royal Society. It was a paper read at the Royal Society in November 1874. And they were all still at sea, of course. So how on earth was that? So there they were, still at sea. The Murray report was years away from being published, and yet here was Thomson describing at a meeting of the Royal Society on November the 26th, 1874, while they were all still at sea. And it was this paper, this is the title of the paper here, Preliminary Notes on the Nature of the Sea Bottom, da-di-da-di-da. And just a couple of lines from the paper here. At station 160 on the 13th of March, the trawl brought up nearly a bushel of nodules from the size of a walnut to that of an orange. And quite intriguing, I think. So this is the Royal Society here on the right-hand side, then in Burlington House, not where it is now. No descriptions, no pictures of nodules in this paper by Wyville Thomson. Lots of all sorts of other planktonic organisms and so on and so forth, but nothing about nodules. So I thought that was really quite intriguing, really. But carrying on the sort of the as I say, this rather tentative chronology, we're up to 1874 now. All of the scientists on board were encouraged by Thomson to do what he did, and that was to write up their work as they were going along and post papers that they'd written at sea to be read out primarily in the Royal Society. And so there are 2 papers here while they were still at sea in March 1876, some by Murray, some by Buchanan, the chemist on board, describing nodules, among other things. And so what we've got here, we've got the equivalent of tweets going on. This is the modern, the sort of the early day equivalent of tweeting your findings as you go along. Much slower time, of course. You know, you had to write your paper, get it posted in some distant port to be then sent by sea, by steamer or whatever. But nevertheless, bringing back, you know, live results, which were then read out in the Royal Society and other places. And in terms of the chronology, I'd just like to end really with something that often, this is a paper, this Buchanan 1878 paper is one that is often cited as, you know, as the first publication on nodules. And the reason I mention it is because it's close to here, Loch Fyne, as it happened. So the chemist on board the Challenger, Buchanan, he went pretty much straight out and carried on doing work around the UK, and he happened to find some manganese nodules in some mud which was collected on the anchor of a boat in Loch Fyne in 100 meters or so, a couple hundred meters of water. And I guess in some respects you might say, well, that's the classic way of producing it. He went out, did the work, and published it in Nature. But there you go. So that's really all I wanted to say, particularly about them. Going back to the reports, well worth looking at. Beautiful thin sections through these things and looking at how the nodules are formed and so on. And this is directly from the plate 17 in that Murray and Raynaud volume. Beautiful analysis being done. These are some of the softer sediments that are being found there, and exquisite drawings and the like. So well worth it. But
thank you.
Oh,
sorry. Thanks, Nick. That's really interesting presentation.
Okay,
and,
good.
I think we're saving questions till the end. Is that right?
Okay. I hadn't quite finished. If that
I'm sorry. Okay.
If that's okay. Sorry.
I'm so sorry. Okay.
Okay, but one of the things that Murray did find were these phosphate accretions, as well as the manganese ones, the phosphate accretions, and this is the final bit of the story about phosphate. Now, a tale of two men here: Murray on the right, Darwin on the left here. Darwin and Murray had a big difference of opinion of how coral atolls were formed. And so they had different theories of how the coral atolls were formed. And one of the things Murray was doing, whilst he was on the Challenger, but also after the Challenger, was to collect samples from around the world to try and prove his theories over Darwin's theories. And one of the things that he discovered was that he was trying to get coral samples in particular from around the world. And in the 1880s or thereabouts, so quite some time after they came back from the Challenger, he managed to persuade a couple of naval vessels to collect some samples for him from Christmas Island. Now, Christmas Island was a very, very long way from where Challenger went. Challenger actually went up through this way, up here. But Murray, was finding samples from wherever he could, particularly of bottom sediments, to prove his theories. What he was able to do was he managed to persuade the Royal Navy to bring some samples back. Now, there were two ships involved here, and Gillen, this is where I think the pictures are all the wrong way around. But anyway, these were two Royal Naval ships. And the first one to go to Christmas Island was, in fact, HMS Flying Fish. They brought samples back. Murray decided that on analysis there, that he realized that they were full of those phosphates that he'd seen actually on board the Challenger earlier. And he would then persuaded a second ship, HMS Algeria, to go and collect further samples for him. And as a result of that, he was able to say with certainty that the area around Christmas Island was virtually pure phosphate rock. And as a result of which, the island was ultimately annexed by Great Britain, and a phosphate mine down in the bottom of the island, this is Christmas Island, phosphate mine was set up. And you'll see here part of the island, Flying Fish Cove, which was where HMS Flying Fish did its first anchoring. And out of interest, you'll see the highest point on the island is Murray Hill. Unfortunately, the phosphate mining company, which was set up jointly by Murray and another gentleman, they did not have the best of, I guess, human relations. Let's put it that way. Lots of labour brought in, but it was a very successful company, and it did certainly make Murray and others particularly wealthy. And very recent photographs. This is Christmas Island. I had these photographs sent to me today, actually. And this is a view of Christmas Island from the air. And this is, in fact, Flying Fish Cove here. Still the signs of the mining company. It's beginning to decline now, but it is still it's still operational. So in terms of legacy, we've got the manganese nodules, we've got phosphate mining. We also do have some very interesting issues around colonialism and the like, which we could get into if we wanted to. But I'm pretty sure that when these guys went off to sea and were doing all their work, they had no idea what these legacies might be. And a particular legacy I know is an important one, which we're going to hear about from Andrew. Thank you.
Thank you again, Nick.
That's it. Have I stopped sharing now?
Yes.
Thank you.
Okay, with that, I would like to introduce Professor Andrew Sweetman, who is with the Scottish Association for Marine Science. And Andrew, if you could give us just a brief intro to yourself, and then you can get right into your presentation.
Yeah, thank you very much, Melissa. Hello all, I'm Andrew Sweetman. Professor, I lead the Seafloor Ecology and Biogeochemistry Research Group at the Scottish Association for Marine Science. And over about the last 20 years, I've been looking at how the seafloor functions and how biodiversity of the seafloor influences how it functions, how it breathes, how the sediments are mixed, how carbon is stored. And going on from that, I also work on how anthropogenic stresses influence the biodiversity and the ecology and the processes that go on at the ocean floor. And in terms of anthropogenic stresses, I've worked on a number of them over the last 20 years, looking at invasive species, fish farming, carbon capture and storage and release of CO2 at the seafloor, climate change. And for about the last 10 years, I've been doing lots of experiments and studies looking at the impact that deep sea mining might have on the ocean floor and also the deep pelagic ocean as well. Can everyone still hear me okay? Yeah, okay. Good. I think you're on mute, Melissa.
Do you want to share your screen?
Yeah, I will share it right now. Can everyone see that? Yeah. Okay. So do you just want me to give this now, Melissa? Is that correct?
Yes, please.
Okay. Well, thank you all for having me and for everyone joining online. I'm going to talk a little bit about deep sea mining, what it actually is, talk a little bit about some of the impacts that we think may happen during deep sea mining. And then I'm also going to talk a little bit about climate change, because very often when we discuss deep sea mining or and debate about deep sea mining, we often don't think about the other side of the coin, which is a lot of the minerals that are potentially going to be mined are going to be mined to allow us to hopefully get to net zero if that's possible, or at least make us a greener species. So just start here. So why is there a push for extracting metals from the seafloor? Well, if you look at the average ore grade that from deposits on land, and you look at how the grade varies as a function of time, what you can see in a lot of types of metals that are being extracted, the ore grade is actually going down. A lot of the high metal content ores have already been removed, and what's left often has less ore or metal within it. So it requires more land-based mining to get the same amount of metal out of the ground that you once were able to. And consequently, when you extract more rock from terrestrial land mines, the amount of waste rock that you're generating actually increases in some cases. So one of the things that people are thinking about is that is there a way that we can get metal more easily if we go into the deep ocean, because the ores that we have on land are not as plentiful in terms of the metals anymore, and it's requiring a lot more waste rock that we've got to do something with as well. And sometimes we dump that rock back into the ocean. This is where mine tailings come from. So deep sea mining is being pushed as potentially one source for these metals. And there are particularly three types of deposit that are being thought about right now. One is the manganese nodules that Nick has previously talked about. Then you have seafloor massive sulfides, which are found at hydrothermal or on the mid-ocean ridge and on back arc spreading centers. These deposits are full of metals like copper, various things like that. And then you also have cobalt-rich ferromanganese crusts that grow at a depth of around 600 to 2,500 meters on the side of seamounts. And if we're going to go out and start mining for these metals, the way that people are thinking about doing it is going out with a surface vessel, lowering a collector vehicle to the seafloor, thousands of meters down. That collector vehicle will either hoover up nodules or it will grind up hydrothermal chimneys that are full of these metals, grind them up into small little particles, and then these particles or nodules will be sent up the riser pipe, where they'll be offloaded to a bulk carrier that will transport the resource back to shore for onward processing. And then sediments and metals and water that's been pumped up from the ocean floor is pumped back down, and at a certain depth it's released. And there is the chance that this plume, this release water, full of sediments, full of particles, that will rain down and start to smother the seafloor environment and also affect animals living in the water column. So this is how people are thinking that deep sea mining is going to potentially happen. And in terms of the seafloor massive sulfides, these are found at the mid-ocean ridges where you find hydrothermal vent fields. I've just returned from the central Indian Ocean, where we were doing some work with the German Geological Institute, the BGR, because they're looking at the possibility to mine hydrothermal habitats on the central Indian Ocean ridge. In terms of seamounts, these are all these dots, the yellow dots that you can see are seamounts between 800 and 2,500 meters, which is where we think there's lots of ferromanganese crusts that are available for extracting. And you can see the North Island of New Zealand here, and then in the top, but about 155 degrees west, you can see the big island of Hawaii. So that just gives you an idea about the size of the Pacific Ocean and where all these seamounts and potential deposits are found. And then in terms of polymetallic nodules, you find polymetallic nodules in the central Indian Ocean. You find them in the Peru Basin, in the South Pacific, for example, around the Cook Islands. And you find them in this region called the Clarion-Clipperton Zone, which lies between Mexico and Hawaii. It stretches over a couple of thousand kilometers. All of these colored shapes, oddly shaped shapes, are license areas owned by different companies and governments, and they have the ability to go out and explore this region to see what the typical ore content is of the nodules at the seafloor, and also start doing baseline surveys and test mining surveys. And I've been involved with a lot of these companies for about the last 10 years. In terms of polymetallic nodule mining, assuming all the nodules within these colored boxes were to be mined and extracted, it would be quite a large area that potentially is going to be disturbed. If you put the Clarion-Clipperton Zone and you just superimpose it on the United States, you see it takes up about 80% of the contiguous 48 United States. So it stretches pretty much from Los Angeles / San Diego to, I think that's probably the eastern part of the state of Ohio. So it's a pretty big area that's potentially going to be mined. But it's unclear how much mining activity will take place at any one time. It's very unlikely that you're going to have tens of mining companies out in the Clarion-Clipperton Zone mining at the same time, for the simple reason that if you have a lot of metal going onto the market, the stock price of the metal goes through the floor, and then it's not economically meaningful to sell this stuff. So it's probably only going to be one or two mining companies actually mining at any one time. But assuming that all of these license areas are going to be mined, it's a pretty big area that could be disturbed. And this is just another image of these license areas over a map of Europe, stretching from around the coast of Portugal into Russia. It's a pretty big area. This is what the seafloor in the Clarion-Clipperton Zone looks like. So what you see here on the left is an image taken by a drop camera. I think we're probably about 4 or 5 meters above the seafloor. And the seafloor in places is just covered with these black potato-sized nodules. They grow extremely slowly. They grow at a rate of about 1 millimeter per million years. And they'll grow in 2 different ways, both diagenetically and what's called hydrogenetically, where they precipitate from metals from the water column slowly over millions of years. And typically what they'll start to grow around is like a shark's tooth. So sharks, they lose their teeth, the teeth sink down to the seafloor, and that forms a nucleus that these nodules can start to grow from. And in some instances, we've actually seen megalodon teeth at the seafloor, which are in the center of some of these nodules. What's also apparent about these nodules is they're really, really important habitats for biodiversity. About 50% of the animals that grow on nodules in the Clarion-Clipperton Zone, we think only grow on manganese nodules. So if you remove those, it's going to be a very long time before the nodules come back. So you're potentially going to lead to a lot of fauna being killed off that might not come back. This is on the right here is a chamber, a benthic respirometer chamber, which I typically use for my research. And here you can see it's about 22 by 22 centimeters in area. And you can see just how many nodules there are in there. The biggest one here is probably 50 million years old. There's lots of animals living on top of the nodules, within the nodules as well. And also loads of animals, enormous biodiversity actually living within the sediments. A lot of the biodiversity, though, is very, very small. But that doesn't mean it's not important. Some of these habitats are very, very low biomass habitats. But the Galapagos Islands is also a low biomass habitat. So, it's you can't just assume that because an environment has low biomass that it doesn't have any importance. Sometimes a lot of low biomass habitats can be extremely important. In terms of how much we know about the Clarion-Clipperton Zone, we know very, very little. So just to put this in perspective, this is the box that you can see here is 300,000 kilometers squared. And it shows all of the records of polychaetes. These are small worms that live in seafloor sediments. And you can see there's over 180,000 records of polychaetes in that 300,000 square kilometer box, centered in the North Sea between the Netherlands and the UK. In 2013, in the Clarion-Clipperton Zone, we had 4. Just to put it in perspective, we have a lot more information now because there's been a lot more studies that have been done in this region because of the potential for mining to begin over the next couple of years. But that just gives you an idea about sampling intensity in continental shelf habitats like the North Sea versus the deep ocean, 4 to 5,000 meters depth. More than 180,000 versus 4 records of organisms in 2013. What are the impacts? Well, in terms of the pelagic zone, which is the deepest, or which is the biggest habitat that we have on planet Earth, the largest habitat we have is the deep sea, and the largest habitat within the deep sea is the pelagic zone. Yet we know very, very little about the deep pelagic zone, far less than we know about the seafloor. But in some recent experiments that we have done, we have collected jellyfish which are found in the deep ocean, Paraphila, and we expose them to sediments and particles that might be generated during a deep sea mining scenario. And what we wanted to do was actually look at, are they affected? So one way of measuring whether they're affected or not is by looking at the respiration rates. And as you can see, as you increase the sediment concentration within the water that these jellyfish were swimming around in, the respiration rate increased, showing that they were stressed. At the same time, what jellyfish do and corals do is, in order to get rid of a lot of these sediment particles that adhere to their bodies, they make a lot of mucus, which is an energy expelling process. When they expel energy, their health decreases. And as you can see in the bottom graph here, the health score of the jellyfish went from 0 with 4, went from a health score of 4, very, very healthy jellyfish, when there was 0 milligrams per liter of sediment in the water column, up to 333 milligrams per liter. You can see that the health score is going down. So these jellyfish are reacting negatively to the presence of suspended sediment. And this is the first time anyone has ever really looked at what happens when you take the deep pelagic zone and then you start pumping in a lot of sediment that might happen during a deep sea mining event. This was a paper from one of my PhD students, Daniela de Jonge, published in 2020. And in this study, we went to a part of the Pacific Ocean called the Peru Basin. And in 1989, that was disturbed by dragging essentially a plow harrow that you use to mix the earth in a field. We dragged it across the seafloor, or scientists dragged it across the seafloor. I was only 9 years old at the time, so I wasn't on board. But we went back in 2015 to this site, and you can still see the plow tracks at the seafloor. This is at a depth of 4,100 meters, about 2.5 miles down. And what we did is we looked at reference sites where there was no disturbance, and we went to inside the plow tracks to have a look at, was there still effects seen 26 years after the disturbance event. And interestingly, we found that yes, the microbes hadn't recovered, and the way that the carbon and the energy was being channeled through the food web was significantly different to at the reference site, showing that mining can have persistent effects at the seafloor. You can see, just look at some of the arrows in terms of DOC, which is dissolved organic carbon here, being channeled to the prokaryotes, the microbes, the bacteria. You can see inside the plow track, very little is being channeled to the microbes, but outside at the reference site, the microbes are having a great time feeding on the dissolved organic carbon. So using these approaches, we were able to show pretty conclusively that mining may have persistent impacts if it goes ahead. The other thing, the nodules that we've seen at the seafloor, they don't just provide a habitat for the organisms living there, but they may actually be vitally important for ecosystem function as well. So this is just oxygen concentration data from in situ. So we've gone down at the seafloor, we've incubated a known area of seafloor in situ, and this is from the North Atlantic, and you can see that when we seal off the sediments, the oxygen slowly goes down as organisms consume that oxygen, and in the process they breathe out CO2, just like we're doing right now. In the nodule province, however, oxygen is produced at the seafloor in situ without any photosynthesis, completely in the dark, completely in the cold. We find that in the Western CCZ, for example, APIs 1, 4, and 7, oxygen is being generated at the seafloor, and we think it's related to the nodules. We think it's related to the electrochemistry of the nodules. They're acting as little batteries, if you will. And what happens is you put a battery into seawater, you get electrolysis, and during electrolysis, oxygen is produced. And this is what we're thinking is happening at the seafloor. So it's a very, very new finding that we're trying to write up for publication right now. So there may be impacts on the pelagic zone, on the water column. There may also be impacts on the seafloor. And these nodules, these habitats, are very, very important in terms of biodiversity and ecosystem function, which we need to be aware of. But why is there a push for mining? You know, if just because there's less, or the ores are maybe less rich in terms of metals, why are we needing those metals in the first place? Well, it all comes down to, at the end of the day, it all starts with atmospheric CO2 increasing as a result of the burning of fossil fuels, the removal of CO2 sequestering habitat like forests, concrete production, those types of things. It all leads to an increase in atmospheric CO2 concentrations. And what we're seeing is that the more CO2 in the atmosphere there is, the warmer the climate is, the less methane you have tied up in a permafrost. So that's released, and it just continues to form a negative feed or positive feedback loop, whereby the climate just warms and warms and warms and warms and warms. So as we probably all know, there's a big push to try to get to net zero by transitioning to greener energies, greener technologies. And this is partially why we're thinking about going into the deep sea to mine. I just want to spend a couple of minutes, these are the last couple of slides, just putting this climate change stuff into some sort of context, because we always think about climate change and it's how it's going to impact us, coral reef, sea level rise, those types of things. But the deep sea, which, as I said, is the largest habitat that we have on planet Earth, relies predominantly on the upper ocean for its food supply. As the atmosphere warms, the oceans warm, the food supply to the seafloor is going to decrease. In some places, as you can see here, it's going to decrease by more than 50% in some ocean basins by 2100. Now, if you think about how much food you eat, if you decreased the amount of food that you ate in a year by 50%, we could probably get by. But just to put it in perspective, the amount of energy that the seafloor, 1 square meter of seafloor gets at 4,000 meters per year is about the same as is in a sugar sachet that you get at Starbucks. That's all the energy they get for a single year. So they're extremely food limited. And these environments, some of them will be experiencing more than a 50% loss in food due to climate change. And that will be global. Okay, it will be global. It's not a small area like the Clarion-Clipperton Zone, it's global. When you decrease the availability of food, the biomass of the seafloor of an ecosystem goes down. The number of animals that you find goes down. The number of species that you find, how it's functioning, it all decreases. It's all reliant on food availability. Where you have more biomass. Where you have less biomass. So by 2100, we're predicting that if climate change keeps on going as it's going, we will lose 5.2 billion kilos of biomass in the deep sea due to climate change alone. And put that in perspective, if assuming each human in Europe weighs 75 kilos, that's about 43 billion kilos of human biomass in Europe. So losing 5.2 billion kilos is the equivalent of losing 12% of the humans in Europe, or 72 million people. When the pandemic happened, as bad as that was, we shut down an entire globe to try to curb people dying. In terms of other organisms dying in the deep ocean, not on land, but in the deep ocean, due to climate change, we're potentially going to lose the equivalent of 72, the biomass of 72 million people by 2100. That's when the effects are seen. That's when this 12% loss is observed, which I'll just get to in a minute. Also, the ocean floor is warming. By 2100, we're predicting in certain parts of the Atlantic, the temperature could go up by 4.5 degrees. These systems do not cope well with big changes in very, very short spaces of time. They're typically used to about a 1 degree change over 100,000 years. Here we're talking about a 1 degree change or a 4.5 degree change in 80. Okay, so these systems are not going to be that good at dealing with both the 50% reduction in food, which is going to be needed to cope with the increasing temperature. The higher the temperature, the more food you need, the more energy you need to eat to cope with that, to increase in metabolism. So, and finally, I'd just like to say that we don't have until 2100 before the deep sea starts to be impacted by climate change. This is data that we did from models that we ran in 2020, where we actually predicted when would the deep sea, the environmental conditions at the deep sea floor, when would it start to go beyond natural variability, to go beyond the variance that these systems are naturally used to in terms of deep sea temperature, deep sea food supply, deep sea oxygen concentration, those types of things. And we found that across large areas of the ocean floor, by 2030 to 2040, they will be being impacted, and you'll be having this biomass lost by 2030 to 2040. It isn't in 2100. We don't have until 2100 to sort this out, because the effects are going to be seen a lot earlier than that. So, yeah, deep sea mining has, it's a potential solution. It has a number of implications that we need to be aware of. But we also need to be aware that the way that we're changing the planet, we are going to lead, if we don't do anything, if we just keep burning fossil fuels and not keeping our pledges that we're coming up with at these COP meetings, etc. In 10 to 15 years, a lot of the habitats in the deep ocean may be irreversibly harmed globally. So yeah, I think that's all I want to say, and happy to take questions. Hope it was clear. Did that?
Well, thank you. Thanks, Andrew. I'll invoke the privilege of the chair to extend our session by 5 minutes to 5 minutes after the hour, so to allow for questions. So the audience, if you have questions, please put them in the Q&A and we can pass them along to our two speakers. Just have a quick observation question for both Andrew and Nick, and it seems as if, Andrew, you're outlining a classic environmental wicked problem, a wicked problem being a problem where one solution to one dimension of the problem exacerbates another dimension. So in this case, the metals, the rare earths, the copper and nickel that might be derived from polymetallic nodules in order to fuel the green tech and an energy revolution for humans would destroy vast swaths of the deep sea bed, say in the Pacific Ocean, where there is no meaningful time frame of recovery for those environments. And yet in the latter part of your talk, you outlined just what the prospects are for the deep sea under the global regime of accelerated climate change. No, it's a classic environmental problem in that it is wicked and it involves trade-offs, a kind of fork in the road where choices have to be made. And for us, the stakes couldn't be higher in that it's a kind of decision that our own descendants will certainly judge us for, and the decisions need to be made now. So more of a comment than a question, but Nick and Andrew, would you like to take the opportunity to reflect on this urgent moment and the decisions that are faced?
Nick, do you want to go ahead with that first, or do you want me to go ahead? Okay. Yeah,
you go first. Yeah.
It is a bit of a challenge that we have. If we don't do deep sea mining, then and we continue to not take our pledges seriously, then potentially the areas that we're not wanting to be impacted by deep sea mining are going to be lost anyway. But at the same time, you don't want to, just open up the entire planet to extraction to get to, net zero. So you've got to do it carefully and think about it carefully, and that's essentially what a lot of my research is doing right now. If the way I see it is that I'm not for mining. I'll be completely honest with you. I'm not for mining, but I'm not against it. Yeah, there may need to be instances where mining has to happen to allow us to get to a position whereby we get this climate system under control, if that's possible now, as it's so late. But the way I feel about it is that if it is going to go ahead, then I want to know that the best scientists with the best data, with the best instrumentation, with the best experiments have been employed to get the data. So if we're going to mine, we do it in the most environmentally friendly way that is possible. Yeah, so that's the way I see it. But the other thing, and this is the most important thing, I think, we have 10 to 15 years. We don't have 2100. That's when all of the effects are seen. That's when we model everything to. But the impacts are going to be, and we're starting to see them now. The impacts in the deep ocean are going to be probably seen and the large areas of the deep ocean are going to be seen in the next 10 to 15 years.
I'm not sure I can add anything sort of to that other than perhaps, I don't know, more of a philosophical point, and that is just by being human beings on this planet, we have an impact, don't we? And the fact that we know of the negative consequences to the extent that we do, actually, I think just forces us to be thinking, that we're still a long way off alternative sources of energy for us. And I think the work that Andrew's doing and others on the negative impacts of mining actually should be forcing us to think that this is not an easy route, because I think a lot of people think actually one of the ways of solving the problem is to make everything electric. And maybe a few years ago, before we knew the impacts of things like deep sea mining, that would have been an okay thing to do. But we now know that even this apparent solution for moving away from fossil fuels, that is, clearly has got its own incredibly negative impact. So I don't have the answer, but I think there are clear enough danger signs here to be saying, look, this is not good enough. Actually, we've got to go somewhere else, or look for something else.
Thanks, Melissa.
Okay, we do have one question here about the Victorians. Did the Victorians consider exploiting the nodules?
Yeah, that's interesting. I saw that question come in. I don't know the answer to that, actually, I have to say.
Well,
maybe Gillen will have a view on.
Yes, I mean, if we go back to Jules Verne's 20,000 Leagues Under the Sea, Captain Nemo, he sees the deep sea as a mining venture waiting to happen. He says from the vantage point of his submarine that there are vast deposits of copper and nickel and iron and just waiting to be exploited. So it's quite, and that, if we remember that Verne published in serial form in Paris, actually in 1870-71, and the first English translation of 20,000 Leagues was published in 1873. Ironically, as Challenger was collecting its first manganese nodules, as Nick pointed out. So the Victorians were aware, and Murray himself was aware.
I was going to say, as you were talking there, Gillen, actually, I seem to remember reading something, actually, Murray making some comments, actually, about the possible use of them, actually. That's right, he did, didn't he? Yeah.
I think we have time for maybe one more question from the Q&A, Melissa.
Yeah, I'm not quite sure. I think it's like a two-part question, but so the essence is that the benefits of deep sea mining may well outweigh the negative environmental impacts, ?
I think if I'm not on mute. I think what I'm what I'm trying to get at is that mining, wherever it occurs, is likely to have significant effects on the biodiversity, the function, and it's possible that recovery will not be possible on our like within our lifetime. But those areas, if we did not mine and we just left them as they were, it's very possible that those areas are going to be lost in the next 40, 50, 60 years because climate change is going to generate so much damage. They will be lost. And areas much greater than the Clarion-Clipperton zone will be lost. I think that is what really scares me here, that if we do nothing and we keep burning fossil fuels and we don't transition to some other alternative as quickly as possible, the deep ocean is going to change so dramatically over the next 70 years, 80 years, that the amount of species, biomass, the functions that the services that we get from it could be lost indefinitely at a time when global population is what, maybe 12, 13, 14 billion. That's what really worries me. So we may have no other alternative in time but to mine certain parts of the ocean, as well as doing other things, cutting down in terms of fossil fuels, recycling more. It's not an easy answer that, oh yeah, let's say no to deep sea mining and no to climate change. If you're going to fight one like climate change, how are you going to do it? And how are you going to do it in the speed that it requires? And it's not an easy thing to think about. I wrestle with this all the time, but there may be a scenario in the future where we just have no choice. But if we're going to do deep sea mining, if we do realize we don't have a choice, I want to know that all of the information about that environment has been gathered so we can make the best call how to do it, what scale to do it at. And then, you can't really do anymore. It's I can live with that.
Well,
I don't
thanks.
know how it helps answer the question or not.
Yeah, thanks, Andrew. Well, we are at the end of our time for today's fascinating and also sobering session. I think there's no doubt that the weight of history is upon all of us here as scientists, educators, and historians, and that the decisions confront us, and also, I suppose, for us as communicators and researchers to lay the groundwork for the best possible decision to be made. So that brings us to an end for the third of our Challenger conversations and wrapping up 2023. We have more sessions planned, more conversation events planned for the new year. The first of which is planned for Thursday, January the 11th. The subject will be research vessels, life at sea, then and now. So please mark that on your calendar and join us for number 4 in our Challenger conversations. I'd like to thank our two guests presenters today, Nick Owens and Andrew Sweetman, and also our special guest, Melissa Ryan. It's been terrific to be able to convene you here online for this kind of Christmas special for our Challenger conversations. So thanks to everyone, and thanks to you all from joining worldwide in the audience, and we'll see you again in the new year. Thank you very much.
Take care.